This lecture is by far my favorite lecture. I think actually when looking at some of the course expectations from a number of you, I saw one of you, when we asked you for your top 3 things that you wanted to learn, you just put sample size. That was it. That was your top 3, 1, 2, and 3 right there. That's great. And I saw that as the #1 priority for a lot of you. So this is, I think, going to be one of the most informative sections of the week. We had a lot of fun putting the presentation together as well over the last few years and revising it. And so I think Rohit, myself, I think Rachel, we all love this presentation. The bad news is that after this presentation and after some of the exercises that you will do, we might see some of the most kind of sudden, unexpected, dramatic changes in our research design. This is the point where we suddenly come to terms with our budget, where we come to terms with having to restrict all of the research questions that we want to ask in our ideal experiment with reality, how many people there are actually in the program, how much money we have to run the experiment, and this is where we need to make some hard choices. So before I introduce Rachel and before we start with the presentation, I just wanted to go over what we've learned in the past few days. So I'd like to ask someone, can someone tell me what are the 5 major components, or if you name 3, of program evaluation? Dave.
Needs assessment, measurement, impact evaluation, I'm having a brain fire.
No problem. Junior, wanna?
Need assessment, theory of change, process evaluation, impact evaluation, cost effectiveness.
Great. Okay. Yeah. So, and usually, oftentimes, measurement finds its way through all of those. Although sometimes the theory of change you can kind of do just at your desk. It's sometimes more of a theoretical thing, and sometimes with the needs assessment, measurement is more qualitative in nature sometimes. Okay, can someone tell me what are some of the reasons why we may want to change our unit of randomization? I'll go to Brian just because you're very active all the time, and then Henry. Yeah.
Contamination, or risk for contamination.
Risk for contamination, yeah.
Mm-hmm. And ensuring adequate sample size to get statistically significant results.
Right, so one gives you a reason why you may want to have a higher level of randomization. Your example is maybe why you want a lower level of randomization, individual instead of school, for example. Okay, great. So I think that kind of reviews some of the stuff that we've covered. Now let me introduce Rachel Glennerster. She's my boss. She's been with JPAL since the very beginning, since 2003. We met in India while we were working on the Read India project, actually. We were kind of traveling through the states of Uttar Pradesh and Delhi and other places, basically trying to figure out what this program that you actually have now seen as part of one of your case studies, what the design should be, working very closely with Problem to do that. So I'll let Rachel introduce herself. She's the executive director of JPAL, and I'll let her talk about some of the things that she does.
Great, thanks Mark, and great to be here. I always love teaching this group of students and hearing about your exciting projects. I'm going to be here on Friday to see you present. So as Mark says, I'm executive director here at JPAL. My background is actually as a policymaker. So I worked in the British Treasury and the IMF and at Harvard Institute for International Development before coming here. But I was always translating, in those jobs, I was always translating research for policymakers. And then I switched to the other side and became, started doing the research and also translating from the research side to policymakers. So while I've been here, I've done randomized evaluations in India, in Bangladesh, Pakistan, and I think my heart is in West Africa, though. Spend a lot of time in Sierra Leone and have done a number of evaluations there. if you ever go to Sierra Leone, you'll understand why the people who have once worked there can never get away from it. And Tom did much of the important work with us, starting on, I think, my very first evaluation in Sierra Leone. Okay, so today I'm going to talk about sampling and sample size, and I'm going to start us off with a question, just to get us into it. Everyone got their clickers? So if you look at these two pictorial representations of 8 evaluations, just, you know, I'm not going to describe it very much, but just if you look at those, which of these two is most likely to describe the results of 8 randomized trials? Which do you think of those is the best description, possibly, of, you know, 8 hypothetical randomized trials? Just to get your brains going in the morning. Okay, polling's open. I've got 16, 17. Oh, I was told there were 19 people, but we seem to have got up to 20. Okay, great. So let's see. So that's great. That's, most of you got the right answer, which is 2. And the reason for that is one of the benefits of a randomized trial is that it reduces bias, right? It reduces, and this is a description of bias. Like, they're all coming up with the same result, but it's not in the center. It's off to the left. So there's some bias there. Everything is mismeasuring in one direction. All of the trials are mismeasuring in one direction, all of the evaluations. Whereas this, they're not all on target, but on average, they're around the true value. So that is a kind of a description of bias. Let me give you another one, which I've slightly given you the answer to, but which is the best description of 2. So if you're trying to describe 2, is it an imprecise estimate, a biased estimate, imprecise but unbiased? Which is the best description of 2? Waiting for one more. Or maybe there really only are 19 people. Okay, I don't quite understand how I got 20 last time, and 19 this time. Anyway, we will go. So, yes, C, we have imprecise. They're not actually exactly on the target, but they are unbiased. They are, you know, some to the left, some to the right, some up, some down. So they're not biased. They're not all pulled in one direction, but they're imprecise because they're not all on target. So this is an introduction to what I'm going to talk about today, which is up until now, you've basically been talking about bias and worrying about being, you know, always pulled in one direction, and you've been talking about selection bias. What I'm going to focus on today is about precision. So how do we get, you know, instead of this kind of scattershot, how do we get them to be in the middle? So, you know, just to give you sort of the 2 directions that we're talking about, you know, this would be, if this is the truth and these are the estimates, then we can think of 2 different directions in which an estimate can be, you know, can be less than perfect. One is it can be biased, and less bias comes with randomization, and the other kind of way of measuring how good an evaluation is how precise it is. So as we increase sample size, we get more precision, and as we move in this direction, you know, say with randomization, but there are other methods that can reduce bias, but we've been focusing on randomization, you get rid of bias But obviously what we really want is something that is both precise and unbiased. So as I say, we've been focusing up to now on bias, and now today I'm going to focus on how do we get to that precise measure too. So I'm going to give a bit of an introduction and talk about hypothesis testing, which hopefully for most people is a review. Yes?
Yes. I have a question. It seems to me that when we look at those two bullseyes here, that we actually know what the true value is. But from a practitioner's point of view, I actually want to do an RCT in order that I know what it is,
Yes.
because I don't know. So if I have a picture like on the upper left side and someone tells me I have 5 studies, that is the absolute holy truth, because
Yes.
that's the gold standard. So
Okay, so this is exactly the problem that we're going to be spending this morning talking about, is when we start off, we don't know what the truth is, right? And yes, this is just meant to kind of pictorially give you the idea of the concepts, but when we actually see these, there ain't no bullseye, right? You see the dots, you see they're all together, and you might be inclined to think, well, they're all together, so they must be right. But they're not, because they're biased. And the only way we can know that is to know that the methodology used might cause bias. We never know whether poor methodology may actually be right, because there isn't any selection bias. Or it may be biased. We don't know. All we see is the dots in real life. You're absolutely true. You're absolutely right. We never see the bullseye. So we have to figure it out from the methodology to know, are we in this position or that position? So if we're in an RCT, we know that and you've dealt with all the threats that you're going to learn about tomorrow, then we know that we're improving on that. If we've got a big sample size, we know we're probably improving in this direction. Because the other thing is, often you don't even see 5 or 8 or however many dots. Like you just see 1. So you don't even know whether you've got a scatter shot. So again, that is exactly what we're going to talk about today. How do I know how precise my estimate is when I only see 1 study, right? So exactly. So just as background to that, we're going to go over hypothesis testing, which hopefully will ring some bells from the past, and then talk about what influences power in a simple individually randomized design, and then in a clustered randomized design, which gets a little bit more complicated. And the second half of the lecture will be, that's all kind of the theory. The second half of the lecture will all be about how you do this in practice, because that's actually very different. The trade-offs that you make, I mean, this is really the skill of doing good studies and even commissioning good studies. It's thinking about the trade-offs. It's not about how do you derive the formula. It's what do you actually do when you're faced with this problem. So I'm going to take an example of a study on school children and looking at, I mean, this is a hypothetical study. We're going to evaluate bringing tutors into schools, right? So we're going to have test scores from treatment group and control group. And these are the test scores. You can see the distribution. Some people get 0%, some people get 100%, very few people get 0, very few people get 100. Lots of people get something in the middle, right? That's the distribution. This is showing how common, how frequently we got these different test scores. Now, we see that then we take the mean of the treatment test scores and the mean of the comparison test scores. Right? I've shown those. And the mean of the treatment group, this is at the end of the study, the mean of the treatment group is larger than the mean of the control group. So is this statistically significant? Is that difference between treatment and control statistically significant? Yes, no, or we can't tell yet. Oh, we got 20 people again. Okay. So, correct, we cannot tell because I've told you nothing else other than what the treatment mean is and the comparison mean is. So, this is what happens when we have one study. We see the treatment group mean and we see the comparison group mean, and we take the difference, and that is our estimate of the impact of the study, of the program, right? Our estimate is simply saying what's the difference between the treatment group and the comparison group. And we get one estimated effect. Now what if we ran a second study? We'd get a second estimated effect. And it might be different. It might be different because this time we have different kids in the class. We have, you know, more of the really smart kids in the control group this time, and so the difference between the two is much smaller, and so we get a different estimated effect size. And any time you run a randomized trial, you may be running exactly the same study, even potentially on exactly the same people, and you will get a different estimate because just things will happen. Someone will have a bad day, they will have a headache that morning, and they'll get a different test result this time than last time. So statistics is about, what happens if we do this many, many times, and that is the best way of understanding the true effect would be to run hundreds and hundreds of trials, and eventually we'd figure out what the right answer was, right? So if we ran many trials, we would get some with low effect sizes, some with high effect sizes, but if we ran it enough times, we would start to see a pattern, a bell-shaped curve and remember, each one of these is another randomized trial, right? And we would start to see that on average, we were getting an effect size of about 5. And that is how we would tell what the true effect is, by running hundreds of trials and seeing that on average we get 5. Of course, we don't ever run 100 trials, so how do we, the challenge is to see from what we get, from the one that we run, what can we conclude? So I'm going to step back and say, we've got to think about how can we tell whether the one that we see is statistically significant or not. And to walk you through the statistics of that, I'm going to talk about hypothesis testing. And we're going to say, what if the true effect was so-and-so? What would we get then? Okay? So that's why it's called hypothesis testing. So we don't know what the true effect is. We're saying what would happen if the true effect was so-and-so. Okay? So this is that same distribution of many, many randomized trials if the true effect was beta, right? Here that's 3. So this is what the distribution would look like. We'd get many trials around 3, but a few times we'd sometimes get as low as 1, and sometimes we would get something as high as 6. Now, if the true effect was 0, we would see that same kind of distribution, but it would be centered around 0. So this was if the true effect was 0, we would get this kind of pattern. Okay? And it's going to be these are going to be normally distributed, and this time around 0. So I'm going to use these two curves a lot to talk about how do we know, what can we conclude from our one trial. So it's really important you understand these curves. This is the distribution of effect sizes we would get if we ran hundreds of trials and the true effect was beta. This is the distribution of effects we would get if we ran hundreds of trials and the true effect was 0. Okay? And critically, they're going to overlap. And that's going to cause the confusion. But as you say, what we actually observe when we run one trial is just one outcome, one effect size. Beta hat, I've said, because that's in economics, we put hats on things when we estimate them. Right? So that's our one estimate. And how do we know whether that one estimate represents a significant effect or not? Did it come from the hypothesis, the set of trials from there being a true effect of beta, or did it come from the set of trials that was a true effect of 0? That's our question, right? We see this one here, this one trial here, and we have to ask ourselves, did it come from this distribution, or did it come from this distribution? Because those are our hypotheses, that there was a true effect of beta or there was no effect. So if you see these distributions of trials and you see this one effect, which is more likely? What do you think is more likely? That it came from the distribution of trials where the true effect is beta, or it came from the distribution where the true effect is 0? David?
0.
So how do we figure that out? Where it crosses this line is the probability. This tells us, the probability that it came from this distribution, and this is the probability that it came from the beta distribution, right? So it's a higher probability that it came from the 0 distribution, because there's more trials getting that outcome from this distribution than there are only a few trials would give you this, such a low estimate. If the true effect was 3, you're very unlikely to get a 1 if you ran the trial. I still haven't told you whether it's statistically significant. We still don't know that yet. We know one is more likely than the other, but that doesn't mean that it's statistically, we still don't know what's statistically significant. So for that, we draw on something called the critical values and significance level. So traditionally, we will use a significance level of 5%, which means that we give only a 5%, something is only seen as significant if there's only a 5% chance that it came by chance. Right? There's only a 5% probability that we got it by chance. So this is the distribution of estimates where where the true finding is there's no effect, right? And you could get some very high estimates even though the true effect was 0. But those are really improbable. So we're going to say anything above this line is there's 5%, only 5% likelihood that came. If you see anything above this, there's only 5% probability that it came from the distribution of estimates where the true effect is 0. Yeah? And that is the critical value. So anything between these lines is pretty consistent with the null hypothesis being true, i.e. that there is no effect. Right? Anything between here and here, it's likely to be that the null effect, there's a pretty good chance that the null effect is correct. So a definition of the critical value is the estimated effect size that exactly corresponds to the significance level. So if we had an estimate exactly here, that's the critical value. The value of the estimate, which is exactly equivalent to where the 5% significance line is. So if we're testing whether the effect is bigger than 0, significant at 95%, then the critical value is the level of the estimate where exactly 5% of the curve is to the right. Right? 5% of this curve is to the right. So let's go back to the question. Is beta hat significantly different from 0 at 5%? No. Why? It's within the critical values, which we said we can't distinguish from 0. OK, so why do we put a high kind of level of proof before we before we rule out the null hypothesis, which in a sense is similar to what we do in the criminal law, where we say you have to prove that someone is guilty, and we assume that they're innocent unless you prove that they're guilty. Well, it's kind of similar in statistics, where we say the presumption is on the null hypothesis, the presumption is on innocence, and the burden is on the prosecutor to show guilt. So, you know, again, in the criminal case, the jury or judge starts with a null hypothesis that the person is innocent, and then the prosecutor has the hypothesis that the accused person is guilty. And in hypothesis testing, you know, instead of the presumption of innocence, we kind of have this presumption of the null hypothesis. So unless you prove that your program is effective, we kind of assume that it isn't. I mean, that's just that's sort of the standard of statistical testing. And the null hypothesis is H0 I'm going to use, is then that there's you know, zero impact of the program, and the burden of proof is on showing impact. No, I would say, you know, we often talk in this way. Sometimes there are other things that are the obvious, that are the obvious null. Like, you could think of the null as being, you know, zero impact. But another example would be, you know, say you're testing a training plus cache, or just cache. The null hypothesis might not be that there's no impact. It might be that there's no differential impact between cache and cache plus training, right? So, you know, the null hypothesis is whatever is kind of the norm, the thing that you have to move away from. Usually that means the program is zero. There are a few cases where it could just mean, you know, this change to the program means that the program didn't change, right? So just kind of clarify on that. So we only, you know, if there's a less than 5% probability, so this is a pretty tough standard. We're saying only if there's a less than 5% probability will we say that it's not due to chance. And then we reject our null hypothesis. And then we can say that the program has a statistically significant impact. So that's what we're saying. When we say it's statistically significant, we're saying there's less than a 5% chance that it's just due to chance. I think. So, you know, there may be cases where the program actually worked, but we still say there's significant effect. We can't say that there's a significant effect. So you've probably heard of type 1 and type 2 errors. I love this picture, which is not mine, as a way of kind of memorizing what is a type 1 and a type 2 errors. So again, if you've got, so a type 1 error is a false positive, i.e. where somebody says you're pregnant and actually you're not, right? So there are a number of ways in which we can screw up when we do statistical testing. This is one of them, right? So again, with a traditional significance of 5%, that means a 5% chance of experiencing type 1 errors, and that's what we're saying. So we're saying we're only letting ourselves 5% of the time say that the program worked when in fact it didn't, or that they were pregnant when in fact they weren't. Now, what if the true effect was beta? How often would we be able to distinguish let's imagine that this program really did work. The question now is, how often will we be able to distinguish the effect from zero? How often would we reject the null if the hypothesis beta was true? Now so this is everything to the left we won't be able to distinguish from zero. So then we're asking, what percentage of the time, if this is true, what percentage of the time will we be able to reject the null? And that is given by the shaded curve. Because anything to the left, we've said, is indistinguishable from zero. So everything to the right is distinguishable from 0, right? So this is, again, this is the distribution of all the times we run these hundreds of trials. And any time we get over this, we'll be able to distinguish it from 0. And this curve tells us how often that will happen. If this is really the true effect, right? So we always have to be saying if this is a true effect. So there's another error that you can make, which is that statistical power, and this is what statistical power is about, is the probability that if there's a true effect, you really are pregnant, that you'll be able to distinguish the effect from 0. Right? So how often when someone really is pregnant will we say, oh, you're not actually pregnant? Right? How often when there really is a true effect will we say that there isn't? That is what power is about. The ability to pick up a true effect when there really is a true effect. Now, in this case, we set a different percentage. Traditionally, we aim for 80% power. Some people aim for 90% power. Okay? So this is an 80% chance that if there really is an effect, we will be able to pick it up. So low power means we may find, oh, that's not right. So this is all the 4 possibilities that we could get. Like when you run an evaluation, you're going to get one of these 4 things, right? You're either, so in one, you could find a significant effect or a non-significant effect. And they could, in truth, really be an effect or not an effect. So you could either have no error, you could find a significant effect, and there really was an effect. You're pregnant, you are pregnant. There's another kind of case where we don't make an error, which is where we find a non-significant effect and there really was no effect, right? Again, no error, that's perfect. So either of these are great. And then these are the 2 errors that people talk about, type 1 and type 2 errors, where it's significant, but there actually wasn't an effect, or not significant when there actually was. And power, which this lecture is about, is the probability that if there is an effect, you find it significant. So the probability that if this column is true, you actually end up in this square. So a little bit more formally, that's the same picture. So what influences power? How do we try and end up in this box? What can we do to end up in that box? So, as we said, power is the proportion of this curve which is to the right of the critical value for the 0 hypothesis, the null hypothesis. So what do you think? So we can see that overlap is a problem. What do you think? Just give me some ideas about how we could get more of this thing shaded. What could happen to the curves to get more of those things shaded? I don't want you to tell me like the statistics of it, just tell me what do I have to do to these curves to get more of this shaded.
They're further apart, so the one to the right is.
Yeah, if this one moves further apart, then there's going to be less overlap. What else could happen to the curves to get less overlap, apart from moving? Yeah, Brian.
They could push up.
Yep, they could be thinner. If they were thinner, we would get less overlap. So that's basically all the things that affect power are going to affect whether they move apart or whether they get narrow or fat. And the further apart, the better. The more power, the narrower the better. So I'm going to go through all the main ingredients of power and tell you kind of how they shift the curves around. Just so you have an intuition of this. Nobody's going to ever have to derive a power equation, but you need to have the intuition of kind of what's moving these things around and why you might get more power and might not get more power. Okay? So the first thing is effect size. right? So this is the hypothesis. If we have a hypothesis that the effect size is small, that's going to shift this curve in, and there's going to be a lot of overlap, right? So that's going to shift the curves. If there's a small effect size, then it's close to 0. There's lots of overlap. And so we draw our significance line, our critical value. You know, this is, and from that we derive the power, and we see there's very little power in this case because the curves are overlapping a lot. Now, if we hypothesize a big effect size, we think, oh, this program's going to have a massive effect. We only need to pick up a big effect. We shift the curve out, and we do the same process, and we see there's lots of power because they're not overlapping, right? Now let's just focus on effect size a little bit more and say, when we're talking about effect size, we're talking about the average effect size in all our sample. Well, what if not many people take up the program? That's going to dilute the average effect size. So even if the people who take up the program experience a massive effect, if very few people take up the program amongst those people we're surveying, then that's going to have a negative effect. So if the effect size for our participants is 3, if only 1/3 of people take it up, then we're back to, you know, a 1 effect size, right? So just graphically, you know, if this is the effect size. If everyone takes it up, but then only 1/3 of people take it up, then the average effect for the average person is just going to be 1 standard error, and we're back to our overlapping curves and low power. So sample size is the next thing that's going to affect our power. Don't look down, because you'll see the answer. Look up. What is sample size going to do to the curves?
Make them steeper, right?
It's going to make them steeper. Oh, sorry, that was a clicker question. I missed it. However, it's asked in a slightly different way, so you can still do it. By increasing sample size U, reduce bias, increase precision, both, neither, or don't know. You increase precision. Yeah, and that's actually a nice way of then thinking about the curves. So now I'm going to ask the curves question. Increasing sample size moves the curves further apart, moves them closer together, makes them fatter, makes them narrower. One more person. Okay, I'm just going to go. Yep, so it makes it narrower. I'll have to edit that out. Good. So this is an effect size of 1 standard deviation and a sample size of 1,000. This would be if the sample size was 4,000. And suddenly, you know, we've got a lot more power. So you see they go from fat to thin because we're much more likely to get the true effect when we have lots of people. The reason that we have these fat curves is because we may just happen to get you know, kids who are doing very well in the treatment group in one time we run it, or kids who are very good at learning in the control group the next time we run it. Well, when you have bigger and bigger sample sizes, you're less likely to have that kind of weird variation where you happen to get all the kids who are good at learning in one class versus another. So the bigger their sample size, the less our estimates change with each time that we run it. We're much more likely to get the same estimate each time we run it, and so our curves get narrower. And with 9,000, they get really nice and precise, and then we have lots of power, even though in this case we've still got a small effect size, right? Variance. What will increased variation in the underlying population do to our estimates? And I'm asking you these questions before I teach you it, so I'm just making you think. So just what do we think? If there's more variation, that means, kids, in some classes, kids are all the same, but in a high variance population, you've got kids who are scoring really well and kids who are scoring really badly. What would that do to our estimate, do to our estimates? Would it increase bias as we have more variation? Would it reduce the risk of bias? Would it increase precision, reduce precision, or it won't have any effect? Okay, you're hitting it out of the park today. So it's going to reduce precision of our estimates if we have more variation because of that risk that we'll get kids unevenly allocated between treatment and control. Now, what does that do to our curves? What are our curves going to look like if we have more variation? A couple of people thinking about it. Okay. So, oh, I misread what you're doing. Yes, it will make them thinner. No, increased variation, it will make them fatter, yes. I need to wear my glasses. So, if you've got more variation, you could easily get a different estimate a different time you run it, because you would get more kids of different kinds, moving from treatment to control. You run the sampling another time, and you happen to get very different kids, and so you get a different estimate. And so there'll be fat, and we know that being fat is bad. Fat curves are bad for power. So the low variance sample, we get lots of power. This is what it looks like with a high variance sample. Big fat curves that overlap a lot. Now, I sort of talked a little bit about this, but let's just go over the intuition of this, because this is, yeah.
I have a question about, it seems like the critical values seem to be changing on both sides. Is that on
The critical values are going to depend on how much sample we have. It's not always going to be the same. The critical value is when 5% is the point where 5% of this curve is off to the right. Right, so that's going to be different depending on whether that curve is fat or thin. So it's going to be, yes, but it's not going to be the same estimated effect size, right? Because if it's very narrow, then the critical value will be very close to 0, right? But if it's very fat, the critical value is going to be way out there. Yeah, in terms of, this is slightly, this is like what the actual estimated effect size would be. Yeah, so if it's close to 0, then you're bringing in the critical value because, most of the curve is going to be very close to 0. But if now it's moved out here, and so the critical value is moved out there. And that's exactly what's causing the problem for power. Is
Okay, so
if
that's the bottom axis is the effect size, not the
Yes.
standard deviation.
Yeah. Because otherwise I wouldn't be able to show you them. Okay, so variance and power. So imagine our program seeks to increase children's height, right? By giving them some, very small children, very malnourished. If you increase nutrition, you get an increase in height, we hope. And there's lots of variation in height in the population. Then at the end line, we see that children in the treatment group are taller than in the control group. But we don't know whether that's because we happen to get the cool children in the treatment group or whether the program led to an increase in height. Right? So that's the problem that variance is causing, and the only way we can do that is to have a big sample size to sort that out. Because otherwise, it might be that we see this in the end line just because we happen to pick the tall kids into the treatment group, right? Now, if everybody looked exactly the same in the underlying population, it would be very easy to sort out whether it was, the distribution of how we allocated the kids or the program that led to that, because we know that they all started at exactly the same height. So if we see that some are taller in the end line in the treatment group, we know that's because of the program. So that's why the variation is causing a problem. Another ingredient is the proportion of the sample in treatment and control. So this is what it would look like if there was a 50-50 split of our sample size between treatment and control. If it's not split 50-50, what happens to the relative fatness of the curves, right? So we know that as sample size increases, the curves get thinner. But if we make one curve thin and the other curve not thin, if we put most of the sample in the treatment group, the control group is going to be very fat, and that's basically inefficient, right? If you want to reduce the overlap, it's most effective to reduce the narrow, to make them narrow in the same proportion. And it's basically because of diminishing marginal returns to more sample size. There's no point in putting all your sample size in the treatment group because the control, this hypothesis is going to be, big and fat, and you can't, you're going to get more of an overlap. So we call this the allocation ratio. The fraction of the total sample allocated to the treatment group is the allocation ratio. Usually for a given sample size, power is maximized when half the sample is allocated to treatment and half to control because of this diminishing marginal benefit of adding sample. In the practical lesson, I'm going to go over the exceptions when that is not the case and it's actually useful to not allocate 50-50. This is just sort of numerically, how you get the standard deviation of a difference between treatment and control. And, if you do half and half, you're better off than if you do, you allocate, 2-2 versus 3-1. You're going to end up with higher variation in the standard deviation of the treatment group. So we've gone through all of the elements of the power equation. This is what the equation actually looks like. Of course, you just bung your estimates into a statistical package and it spits it out. So you don't actually ever have to solve this equation. But we've got the effect size, the hypothesized effect size, power, significance level, variance, sample size, and the proportion in treatment. So all the things we've talked about go into this equation. Now, that is for a simple, individual-leveled randomized trial. What about clustered trials? And this is where people make mistakes most often, right? Because it's not the same thing. So let's just review what the difference is between if we randomize individuals to treatment and control. You know, we take the individuals, we randomize them treatment or control. But if we do a clustered, for example, classes, we're putting people into clusters, and then everyone in a cluster is treatment, and everyone in a cluster is control. So compared to an individual level randomized design, to achieve the same power, a clustered level RCT is likely to require a smaller sample size, a larger sample size, the same sample size, or you don't know. Just gut feeling at this point. If we have exactly the same number of people in an experiment that is individual versus one that is clustered. Sorry, I'm saying that the wrong way around. To achieve the same power, will we need more people, less people, or the same number of people? Will we need to interview the same number of people, more people, or less people, if we want to get the same power? Okay. We'll need a bigger sample for a clustered trial. Now, why is that, and how exactly does that fit in? Well, just to give you an intuition, imagine we wanted to know what the effect of, what the outcome of an upcoming election would be. We could randomly select 50 people from the entire US population, or we could pick 10 families and ask 5 members of each of those families. You know, I think most of us would realize that people within families may well vote the same way. Not always, but you know, there's some likelihood of that. And therefore, if we select 50 people, we get a better idea of what's going on than just selecting 10 families and interviewing 5 people in each family. But what matters for how much using a cluster design influences power is how similar people are within clusters. And that we define using the intra-cluster correlation, or rho. So to explain what that is, we have this population of very different kinds of people, some with red hair, some with blue hair. And that population lives in clusters. Families, they may, or firms, they may, cluster in schools, neighborhoods, many, many different kinds of clusters in our lives. This is low intra-cluster correlation, right? Within the cluster, there's not a lot of correlation between people. They kind of pretty much look like the population. Now we're going to sample some of those clusters to understand what the population looks like, and pick some for treatment and some for control. And we'll kind of be okay because the treatment and control are still looking pretty similar. They're looking pretty similar to the population, and they're looking pretty similar to each other. So we've still got a valid treatment and control. If there's high intra-cluster correlation, that means this population lives in clusters, works in clusters, is educated in clusters, where everyone is similar to each other. Then we have a problem, because we pick a few of the clusters to be part of the study, and we pick some to be treatment and control, and they look nothing like each other. Right? So that's where we have to worry about doing clustered trials. So I'm going to go through the definition of intra-cluster correlation. So the total variance in a population is made up of both the variance within a cluster and between the cluster. You can kind of see that those add up to the total variation. You either have the variation within the cluster or between the clusters. When the variance within the cluster is small, the within cluster correlation is high, right? Variance and correlation are kind of the opposite of each other. And ICC is high, and that's what this looks like. So the definition of ICC is the proportion of total variance explained by within cluster variance. Okay? So this is the formula, but really the concept that you're worrying about is how much of the variance is within the cluster, how much do the clusters look like each other, or are they really different from each other? How much do people kind of live with or work with people who are similar to them? And the more of that you have, the worse it's going to be. That's basically the main intuition that you have to take away from this. So how does ICC impact power? For a given n, for a given sample size, which is the number of people. Yeah.
So with variance, are we talking about sort of expected variance in the actual outcome, or variance in
no variance in the population? When I talk about variance, I'm saying how different are people.
So just general observable characteristics, or sort of anything, not necessarily directly.
Yeah, anything. Well, as we'll get on to, what matters is the variance that's going to affect our outcome. You know, I talked about height, variance in height, when we were worried about how the how the program was going to influence height. That's the worst kind of variance, where there's variance in the outcome that we're going to measure. So that's the thing we're worried about: variation in the outcome of the study, right? So if the outcome is focusing on height, we're worried about variation in height in the underlying population because of this concern that we may be seeing what we see just because we happen to pick people of a certain kind. And if everyone was the same, that would never be a problem. If everyone was absolutely identical at the beginning and in their trajectory, in their growth trajectory, we would never have to worry about variance.
So, I mean, I guess if there are multiple sort of characteristics for which there can be variance, do you do that equation sort of over? Does that make sense? So if both height and nutrition are varied within sort of populations, but they're maybe independently varied, is there?
Well, what you use in the power equation is the variance of the outcome that is going to be your outcome variable. So, your effect size, if your effect size is height, then you're worried about variation in height. Yeah? You may, in general, you may not necessarily have a measure for that, but you see, see things that are very correlated, and so you may not observe at the beginning your final outcome, and you may worry that if you see variance in something else, that's going to mean variance in your underlying outcome. But specifically for the formula, we're talking about variance in the outcome of interest. That's going to be our final measure of effect. So, if we see all uneducated people living in one place, people with only primary education living in another village, and all college graduates living in a third neighborhood, then ICC on education is high, low, or that's nothing to do with the ICC. Yeah, so we're getting, that's a high ICC. So if ICC is high, what is the most efficient way of increasing power? So if people are very similar within the cluster to each other, what's the best way to increase power? Is it to have more clusters, or interview more people within a cluster, or both? Or you don't know? Again, I'm asking you the questions before I teach you the answer, so. Okay. So this is an interestingly worded question. More efficient. Both will increase power. Both A and B will increase power. Getting more clusters and more people within the cluster will increase power. Is more efficient in the sense that we get more power for less money by increasing the clusters. Because that's what's screwing us. Like if everyone within, in the extreme, if everyone within a cluster is exactly the same, we only need to interview one person and we've got it. Like the second person tells us nothing. Now, it's never the case that they're exactly the same, but you know, just the extremes help to understand the concept. So the equation for power is the same as without clustering, except that we have to add the average size of the cluster, how many people we're going to interview in a given cluster, and this intra-cluster correlation. And when you start working on this, if you're doing cluster designs, you're going to see that this is going to have a huge impact on your estimated power is whether you're clustering, and if you're clustering, how many people you're doing per, and in particular ICC. You've seen the equation, as I say. What you actually do when you do power analysis is you plug numbers in, and the statistical package will spit out the result. But what do you plug in? Like, what numbers should you put in? As we say, when we start, we don't know the effect size. We don't know, how do we figure out what the variance is? Where do we get these numbers to do the estimation? And what are some of the trade-offs that we have to make when we're in the middle of doing a design? So that's what I want to talk about now. So this is the basic steps that you go through when you do power analysis. You set your desired power. Usually we do 80%, significance 95%. Right? That's the easy stuff. That's just what we do. Those are just traditional numbers. Then you need to get hold of some data that is relevant to your population. And that might be from a study somebody else has done. It might be from national statistics. It might be from pilot data. Pilot data is a little bit of a problem because it tends to be, it's a pilot, so it's small. So you may not get very accurate measures of things like intra-cluster correlation and variance. So usually we usually use data from other studies or national data sources. And we calculate variance of the outcome of interest and intra-cluster correlation if we're doing a clustered design. Okay, so you just take this data and you calculate it, you run it through put the numbers into Stata or R, and it spits out variance and ICC. Then we decide the number of treatments we want to do, and we set the minimum detectable effect size. I'm going to come back to that a lot. That's going to be one of the most important things judgment that we make is the minimum effect size we want to be able to detect between treatment and control. We decide the allocation ratio. We're going to split the sample 50-50 between treatment and control, probably, and calculate the sample size. And most textbooks would then say you're done. Okay? Then we estimate the budget, and we realize we can't afford it. I don't think there's ever been a study where I've done that and I'm done. Like, never. Like, the way it's presented in textbooks is, you calculate how much sample size you need, and then you go do it. Well, there's always constraints on the amount of sample size. It may be the budget. It may be the fact that the implementing partner can only do 50 schools, right? So there's constraints on our sample size. So we go back. and we say, what can we cut? What can we change? How can we change the design to get more power? Maybe we cut a treatment arm. Maybe we decide to randomize at the individual level instead of the cluster level. We go back and we adjust, and we repeat until we come up with a design that makes sense. So this is not a one-off thing. It's like you go round and round and round, and it informs your design. And it's not like you do your design and then you do your power. You do your design and then you do your power, and you realize it's wrong, and you've got to go back and change your design. And that's kind of the process that we all go through. So let's think about some of the things we have to worry about as we go through this process. Yes?
I missed this from the previous slide. What is MDE?
So we talked about effect size, the hypothesized effect size being important in power. So that's what we're talking about. We're talking about the effect size. But as I'll go into a lot more detail about how do we come up with the right effect size. What effect size should we be putting in there? But the name of the effect size we put in is the minimum detectable effect size. And that name actually tells us everything we need to know. It's the minimum that you will be able to detect. Okay? So, and that's going to take a lot of judgment to figure out what that should be. Let's start with something slightly easier. Variance, right? So we know that variance is important, so we need to get a good accurate estimate of what the variance in our underlying population is. There's not much we can do about variance. Like, it is what it is. Like, if the variance, if the height varies in the population, that's what it is, okay? Remember that our problem with variance is that if we see differences between treatment and control, we don't know whether that's because we happen to get tall people in treatment versus control. So what might we be able to do to solve that problem, to help us distinguish? Well, again, our problem is at end line, we see taller people in treatment than in the control, and we don't know whether that's because of underlying population variance and happening to pick taller people, or because the program worked. What can we do to try and sort that out? One thing we can do is to get a baseline estimate and see whether we happened to pick taller people in treatment than in control at the beginning, and it looked like maybe we did in this case. And then we can account for this when we do our estimation, and accounting for the baseline gives us a more precise estimate. So what do I mean? I mean, we're going to include in our final estimation the baseline level of height. Right? And then we're tracking this kid over time from the baseline to the end line. And we can see that in the control group, while there's people of different heights, this kid started small, ended small. This kid started tall, ended tall, right? Now in the treatment group, we again control for the height at the baseline, and we see that this kid started quite tall but ended up even taller. So we see that there's a change in height in the treatment group and not a change in height in the control. So we're helping to solve some of the problem of variance because we can tell how much of the difference at the end line came from difference at the baseline. David?
Is that always going to solve a variance issue, or to take the baseline data?
It's going to improve the variance issue, the variance problem, because we're helping to explain some of the variance. So what we actually put, if we want to refine things, what we actually put in the power equation is not variance, but residual variance. The amount of the variation I cannot explain from everything else that I know about this population. So again, the reason variance is a problem is because of the risk that we may happen to pick successful kids for the treatment group. But if some of that variation can be explained by other factors, we know that older kids tend to be taller, we know that men tend to be taller than women, we know that educated farmers tend to have higher yields. Any of that variation in our outcome that we can explain by observable factors is not going to be a problem, because we know that's not because of the treatment. So we can wipe that out, and we're left with the unexplained variance, and that's going to be the problem. Yeah? I mean, there's always uncertainty in the unexplained, but that's part of the equation too. That's part, right? So using controls, so it may not be baseline, it can be other controls, but anything that soaks up variation, that explains variation, means that we don't get confused in the final estimation. It increases the precision of our estimate. And given that we're going to have a more precise estimate, let's know that at the beginning, and let's figure out our sample size based on that, right? So we calculate residual variance by regressing the outcome on controls in the existing data. So if we have a national survey of, you know, that has height and kids' ages and their gender, and even maybe their income levels or their ethnicity, you know, we run the regression of all the things that we will have in the final endline data. So we have the outcome against a whole bunch of controls that only the ones that we will have in our endline data. We kind of mimic the regression we're going to do at the endline, and the residual variance is then what we put in. And on the whole, baseline variables tend to be the best control, because they already, you know, the baseline level already takes into account the kid's age and the kid's gender and their ethnicity and whatever. So it's kind of all summarized usually in what they were in the baseline. I mean, that's not necessarily the case, but just having done a lot of these things, usually you don't get that much better than just putting the baseline value. Yeah.
Quick question. How often do you in practice start again if you see that in the baseline the treatment and the control have different values?
Good question. Have you done stratification yet?
Well, we talked about it.
We talked about it, yes. So in practice, what we do is we make sure that we've stratified so that never happens. A, we've stratified enough, and B, we have a big enough sample so that never happens. Now, and that's partly because the statistics get a bit hairy if you randomize a second time. It used to be the case that people would randomize differently. They used to randomize 100 times, pick the 20 times where it's balanced, and then randomize which of those 20 they used. That was a very standard way of doing RCTs. The econometricians came along and said, we're not completely sure what you're doing when you do that. You may be forcing correlations that we don't quite understand. That may slightly bias your estimates of the standard errors at the end. Please don't do that anymore. So I don't think practically it's a huge problem, but you know, if there's anyone out there who says it's not valid, then it's a bit risky to do it. So now we kind of stratify the hell out of things so we're not in that situation. Now, there are times, including a time 2 weeks ago for me, where we had a very small sample. There's nothing we can do about it. We are randomizing at the level of the radio station. There simply aren't that many radio stations. Like, we can't, you know, that's an example of sample size. Like, there's that many different radio stations in the country we're working, and that's the best country to do an evaluation of radio stations. So we're stuck. So it was a bit hairy when we did that randomization. It could have been that we got unbalanced. We got baseline data on everything. We worked incredibly hard to stratify as much as possible, but there were only a few radio stations, so there was only a limited amount that we could do. if that had turned out really badly, I would have re-randomized. Because for me, I felt like it was worth the risk of some econometrician saying, well, maybe the standard error is slightly different, versus if it was completely different between treatment and control, and you then spend like $1 million doing the RCT, I mean, I just wouldn't have done it. And I've seen people who've gone ahead in that situation, and I don't think that was the right decision. But the real answer is don't do RCTs with 18 clusters like I'm doing, and you know, stratify the hell out of it. And we put months of work into coming up with innovative ways to stratify, which you didn't go over yesterday. And so we were actually fine. And that's really the answer. Okay. So just coming back to this, doing the baseline. Within Stata, I don't know R as much. I assume there's a similar command. There's a command where you say that you're doing several rounds of data, i.e. you're putting in baseline data, right? So you're controlling for your baseline level. And then it prompts you for another question, which is, what's the correlation between, over time, between these variables, right? So if putting in a baseline is going to soak up variation, it needs to know kind of how much it's soaking up. So, so it's going to ask you, if you put in baseline data, how much you're changing, how much that then explains the next round of data. So just be aware, and again, that's something then if you're doing this, it can be quite hard. You've then got to find data in a similar sample that is not just one round, but is 2 rounds, so you can calculate how much height last year predicts height this year. Yeah. So estimating rho. This is our intra-cluster correlation. Rho has to be between 0 and 1. Remember, it's the proportion of variance. It's a proportion, so it has to be between 0 and 1. Really depends a lot on the context in which outcome variable. You know, some outcome variables are can be very correlated within area. Some aren't. Now, to estimate rho well, to estimate how much people are similar within groups, you need a lot of data. So that's why it can be a problem to get it from pilot data. And your power calculations are going to be very sensitive to that number. So when I do power calculations, I estimate it, but then I also look at, well, what if my estimate of rho is wrong? What if it's a little bit bigger? What if it's a little bit smaller? And I do a whole bunch of different calculations to see how sensitive my power and my sample size estimates are to different possible rhos. So here's just some rhos from different studies we've done, just to show you how much it changes. So I was doing a lot of work on agriculture, so there's quite a lot of agriculture in there. You know, household production of maize, very low. Household production of cocoa, very high. Why? Because cocoa can only be grown in very specific climate areas. And so, you know, some parts of the country, there's not going to be any. Some parts of the country, everyone's going to be going cocoa. Rice yields, for some reason, yields actually tend to be very different in different, you know, within the same community. You have good farmers and bad farmers. This is quite interesting because test scores are all very different in different places. Like sometimes test scores are very correlated, sometimes they're not very correlated, so you really need to know that from your context. Got Texas precinct voting preferences kind of in the middle. Hospital admissions, you know, people, that's very different, so very low. Intra-cluster correlation, as is weight and cholesterol, was again another test score, which is, you know, reasonably high. So this is just to say, like, it really depends. There is no standard rho. Like, it really, really depends. And I think from our intuition, we can see that some things, you know, people are very similar. within clusters and some, it really depends. What's the cluster, what's the thing? Treatment arms, big decision that you have to make. Very big impact on power. The nice thing about having lots of treatment arms is that we can really disentangle mechanisms, so we don't just test the program, we see, what if you did it this way, what if you did it that way? Is it the cache, is it the training that's driving the result? You can really take apart a complicated program, test the little bits on their own, put them all together, see if there's complementarity between different parts of the program, all sorts of fascinating things. And I see people get excited when they're designing these and they want to do 15 arms, and you can't do 15 arms because of power. So lots of arms requires lots of sample size. You also have to start thinking about different effect sizes that you want to pick up, because the effect size between one treatment group and the control group may be different from what you want to pick up between treatment 1 and treatment 2. Especially if treatment 1 and treatment 2 are pretty similar, they're just slightly different, then you might need to pick up a slightly different effect size, right? So it's going to be different for comparing treatment and control versus comparing treatment 1 versus treatment 2. Okay, I'm not going to delve into an example to look at how do we think about multiple treatment arms and how that compares, how we think about the effect sizes also. This is a project I have been working on for 9 years in Bangladesh, and it is looking at child marriage. This is the kind of needs assessment. So this is from national level data, and you get the percentage of girls completing secondary school, 9% in 2007, 19% in 2011. The percent of girls who are married before the age of 18, 66%, 65%, no real decline. So the majority of girls are getting married while they're still kids. They're giving birth as teenagers. In our population, 1/3 of the girls are stunted, so you've got to think of a 15-year-old with the body of a 12-year-old giving birth. Not a good idea. Very low levels of contraception use, and very high levels of giving birth at home. So very low utilization of health facilities, and in general, a picture of a need for, I would say, women's empowerment. So we were working with Save the Children to look at programs to address those issues, and this is what we came up with. One is an empowerment program where girls work in safe spaces after school. So about 3 to 5 times a week, they're meeting after school, usually in a friend's house, 20 of them, and they're going through a program. They look at where they're taught about gender attitudes, literacy, health information, sort of livelihood skills, and they go through that curriculum for 6 months. That's the basic treatment. Kishri Konta is the name of the program. Some then got a livelihoods program where they're taught basically financial literacy with the idea that if you, this improved negotiation skills, but here is, if you can be more economically active and valuable to your parents, maybe that is the way to empowerment. Maybe that is the way, your parents may value you more. Maybe you have a little bit of money to help you stay at school, etc. And half of this group received saving clubs as well, where they were encouraged to save. A very different approach was to give a financial incentive to the parents to delay the marriage. So this is a setting in which parents have to pay a dowry when their girl gets married, the dowry rises with age. So if you marry your girl, if you delay the marriage of your daughter, that comes at a big financial cost to you. So this incentive was designed to offset that financial cost to the parents. It was given because Save the Children didn't want to hand out cash. It was given in the form of cooking oil, which is just something that everyone has to buy, and therefore you get it for free, and therefore it's sort of equivalent to cash. And the full group are the group that gets this basic training, financial literacy, and the financial incentive. So this is kind of throw everything at it group. And this is, and then we have a control group. And these are the number of communities that were randomized. So 76 communities get this, 77 get financial literacy, and we end up with 460 communities overall. So we have 1, 2, 3, 4 treatment groups and a control group, and then we did a crosscut, which is we take half of this group and half of this group and add an additional treatment, which is these saving clubs. It doesn't actually use up any more sample size. But it comes at a certain cost, but I'll just explain, let me explain, you know, what are the hypotheses we're testing with this many treatments? And then, for each hypothesis, we have to calculate power, right? For each different comparison, right? So the first one is, does the basic program have any effect on our outcomes, our age of marriage, and staying in education? Those are our basic main outcomes. For that, we compare the treatment 1 to the control group, okay? Notice I have an unequal allocation here, right? I've got 153. You'll see why in a minute. So I do one power calculation for that. The next thing I want to do is what's the marginal impact of adding financial literacy to the program? For that, I'm going to compare treatment 1 and treatment 2. So the effect size I'm going to try and pick up is just the marginal impact of those two. Right? And now I've got less power because I don't have this nice big control group. I'm comparing 76 to 77 groups. So, you know, once you start doing these multiple treatment groups, you've got to do the power thing for all these different hypotheses. Now, some of them are going to be the same. Every time I compare 76 to 77, it's going to be the same, right? But they are going to be different. Now, the other thing that I can do, and this is why I have the bigger control group, is that I can ask a question of, if I combine these two and just say, did KK work? Like there's 2 different versions of KK. I'm just going to combine them into one group and say, did it work? And when I say it, I mean half of them getting financial literacy and half of them not, but, you know, overall, did it work? And we're doing the analysis now, and for most outcomes, not all, but for most outcomes, we're getting a 0 here, but we're getting a very precise 0 because we're getting 153 versus 153. Like, so when I'm thinking about my treatment arms, I'm thinking about, can I pool them and get a really precise number from a pooled comparison? And similarly, we find that these 2 groups delay marriage. The financial incentive is effective in delaying marriage, but you know, when we're designing it, we're hypothesizing if that happens. Well, if we want to look at the effect of delayed marriage on things, again, we have a nice fat sample to look at because we're comparing 154 to 153. right? So there are some things I can answer the question much more precisely than others, and I think that's important when we're doing those complicated designs. Now, then my savings design, I'm going to take half of this and half of that and compare it to the other half and the other half, and that's going to give the marginal impact of savings clubs. Given all the rest that else is going on, and I can't in any way, I'm never going to be, it never was my intention of being able to compare, you know, this versus this versus that, that's going to be too small. So I'm making the decision at the beginning. There's some individual cells in there I'm not going to be able to distinguish. I'm only going to be able to pool those in savings and those without savings, and that's what a cross-cut design does. Cross-cut is where you're not worried about the individual cells, you're just, you're taking half of everything and comparing them, but you won't be able to do each individual cell. So these are all trade-offs that you have to make about what's the question I want to answer, what question do I want to answer precisely. And power is, we aim for 80% power, but we may sometimes want to throw in a question knowing that we're not going to have much power, but hey, a 50% chance of being able to answer it is kind of useful. I wouldn't design a whole RCT around that, but there may be cases where I'm willing, if I'm going to answer a whole bunch of questions, I may just throw in a question that I know from the beginning I only have 50% power, a 50% chance of answering. So, what are some practical tips from having done this many times? You really want to have at least one intensive arm. What I mean by an intensive arm is one where a zero would be interesting. I have done lots of RCTs and got lots of zeros, and sometimes the zero is interesting, and sometimes people say, well, if we'd done it, it would have worked. Well, it was only this long. Well, that's really, then you get a zero and it's not very interesting. You have to always think when you're designing these things, there is a chance I'm going to get a zero. And if I get a zero, is it going to be interesting enough? Now, what does that mean? The program was had a sufficiently high, people thought it was going to work, or enough people are doing it already that it's interesting that it doesn't work. And the other part of being a zero being interesting is it has to be precise enough. Because if all you're doing is saying, I can't distinguish this from zero, but it could have had an effect, but I couldn't have found a big effect. It could have had an effect, but I couldn't pick it up. I can't distinguish it from zero, but there's a massive standard error around it. That's really not interesting. The only thing that's interesting is a precise zero. You can rule out that this had even a marginal effect. That is interesting. If you can say, well, I can't distinguish it from zero, but it could have been big, it could have been negative, I don't really know, you shouldn't have done the trial. In the analysis, as I've said, it may be useful to pool some arms. So think about that when you're doing the design. What would be an interesting pool? And that pool will be measured very precisely. And often we pool any treatment. The different treatment might be slightly different varieties of treatment, but think about creating an any treatment arm. So another trick, another tip, is you have to think about what the sample size is giving you in the different statistical packages, right? Because if you've got multiple treatment arms and the statistical package may not know that you're doing multiple treatment arms. So what do I mean? Stata gives you the sample per cell. It assumes that you're doing treatment and control, but then it says, this is how much you'll need for treatment, this isn't how much you'll need for control. Well then, if you've got 3 treatments, you have to multiply by the number of treatment arms you've got, right? So, when we use the term cell, we mean the number of treatments plus control. So something that has 2 treatment arms and 1 control has 3 cells. So if you put it into Stata and Stata says 90, you know, it says 100, that they're meaning 100 treatment and 100 control and 100 for the other treatment group, right? So it's 300. So just the different packages will present it in different ways, but just be aware of that. So optimal design, as they say, I think it assumes one treatment and one control, and they will just give you the overall sample size. And so you have to divide it by 2, and that gives you the number per cell. So Stata and optimal design do it slightly differently, so just be, you know, really aware of what it is that you're getting. And given that, and as they say, apologies, R is not, I haven't used R very much so far. I promised you that there would be cases where unequal allocation, where it might be the right thing to do an unequal allocation ratio. So you just saw an example in my Bangladesh study where you're going to pool it, and therefore unpooled, it's going to be unequal, but pooled, it's going to be equal. The other important case is when you have a certain amount of money, and that amount of money is going to be spent on both the implementation and the evaluation. Now, why do we want an unequal allocation ratio then? Because adding one person to treatment is going to be much more expensive than adding one person to control. Because when I add someone to treatment, I have to pay for the treatment and the survey. And if you're talking about admin data, which you often use in the US, adding someone to the control may cost like nothing. So then why not put a whole ton of people in control? Like it'll increase your precision a bit and it doesn't cost you anything. Whereas adding someone to the treatment, it may be a very expensive treatment, and that's going to it's going to really cost you a hell of a lot. So it may make sense. So the reason that we normally go for 50-50 is one more person in treatment, one more person in control gives you equal amount of, you know, extra power. But that ignores, that's assuming that you've only got, that it costs the same to add one person to treatment and one person to control. If it costs you, you know, 5 times as much to add someone to treatment, you're almost certainly going to get more power after adding 5 people to control than 1 person to treatment. Well, so you could figure out a formula that would tell you, you know, what's the cost of adding it, and some of our affiliates have done that. But what I do is I just try different treatment. I try different allocation ratios, and sort of you'll see that basically initially you'll get it'll be fine. You know, adding a few more people, you don't lose much from being slightly unequal, and then you lose a lot when you're really unequal. So, you know, just try it with different treatment allocations, and you get pretty quickly get a sense of where you're really getting diminishing diminishing benefit from adding more and more people, say, to the control, and there's really, you know, not much benefit. And you can just try out the budget of doing different allocations and power, and try and get a sense of, you know, what's the right optimal allocation. The other thing, the other tip, is to put your money behind your most important question, right? So when you've got multiple treatments, put more sample in the question that you care most about. Again, you know, pooling treatments, if you're going to pool treatments, then make sure you have a nice big control. And if you really care, if the main point of your analysis, the main point of doing this is to compare the difference between treatment 1 and treatment 2, then you don't want it all in control. You want to put it in the treatment groups, because if, you know, the key issue is comparing treatment 1 and treatment 2, then you need treatment 1 and treatment 2 to be big, because control isn't coming into that decision, into that trade-off. So it's all about where you know, what's your most important question. So yeah, we talked about that as an unequal allocation ratio. And in the end, it turned out, you know, we didn't have a huge amount of sample to compare between this treatment and that treatment. I mean, you know, this is a massive sample project. overall. We've got 11,000 girls in detail and many more that we get some data from. But in the end, these two have zero effect, so I'm not really interested in whether one's bigger than the other because they're both zero. So, okay, so now we're going to go in detail on minimum detectable effect size, but I'm just going to get your sense at the beginning before we start it, your views. What effect size should you use when designing your experiment, when you're doing the power calculation for designing your experiment? What effect size should you put in to that equation? The smallest effect size that could still be cost effective, the largest effect size you expect your program to produce, both, neither. They're kind of different, so I can tell you now it's not going to be both. So I'm going to argue that it's the smallest effect size that can still be cost effective is particularly important. Let me explain why. What is this minimum detectable effect size? I've been talking about it all the way through, but this is really the critical design question. It actually, like if you look at the formula, it has the biggest effect on the sample size when you're calculating your power. Like everything else was a square root and this wasn't. So it has a really big effect. It's not the effect that we want or expect. That is not what you want to plug in. Right? And that everyone does this. It's wrong. That is not what the minimum detectable effect is. It's the minimum detectable effect size. It's not what you hope the program's going to achieve. It's the effect size. Think back to what we were doing with those curves. It's the effect size below which you will not be able to distinguish the effect from zero, or with 80% probability, right? Even if it exists. So what does that mean for what it should be? I.e., it's the effect size below which it might as well be zero. And that is a policy question. It's not a statistics question. Right? How big does this program have to be to actually mean something? Because that's what I want to be able to pick up. If it's smaller than that, it might as well be zero. That's what we're saying. We're saying we don't want to pick it up if it's smaller than that, because it doesn't really matter. Right? Because if it's below that, you may have a high probability of saying, I can't distinguish, it's not statistically significant, and people, they shouldn't, but people are likely to respond saying it didn't work. Right? Statistically, what we're saying is we can't distinguish it from zero, but that'll go out there and people will say, well, it's not significant. This program isn't significant. So you don't want that to happen unless the effect is so small that it kind of might as well be zero. So the kinds of questions you need to ask yourself when you're setting the MDE is, below what effect size would the program not be cost effective? Because if it's smaller than that, it might as well be zero. Like if it's not going to be cost effective, if it's that small, then it might as well be zero. How big an effect would you need to make the result interesting? Again, like if you give people, a huge amount of money and it doesn't have any effect, that's kind of interesting. So, how big an effect would it need to be to make the result interesting? You may want a smaller MDE between treatment arms than between treatment and control. Again, if you really care about distinguishing this version of the program than that version of a program, well, how big a difference would you need for that to be relevant? That may be smaller than the question of whether it overall has an effect. Right? If a slight tweak to the program could have quite a small effect and still be worth it, because it's not costing you very much more to do it slightly differently. So that would suggest a very small MDE between treatment arms. As I've said, you know, that comes with lots of costs, but again, that's what you've got to ask yourself. So a common mistake is when doing a power calculation is simply to look at the MDE between treatment and control and not think about what's the relevant MDE between treatment groups. And I see that all the time. Okay, so we think of, you know, power equations. Again, this is what you get in the statistics books. You do the equation, you do it once, there's one thing. Well, that's not actually how it works. Often, we've got many outcomes that we care about. So then you need to do the power analysis for all the different outcomes that you care about. So this is what my power table looks like in my application for funding for that Bangladesh study. It's a little complicated. It's not one number. Right? So what have we got? We've got all the different outcomes I'm going to measure, and they all have different power. There's no point in putting the sample size there. Like, the thing that you want to put is the minimum detectable effect size, because the sample size, you said, this is my sample size, and someone have to judge whether it's worth funding this study. So what do we put? We put the minimum detectable effect size. How big an effect will I be able to pick up? Is this precise enough to make this study interesting? So I have the other thing you remember. Sometimes I'm comparing 77 to 77, and sometimes I'm comparing 154 to 154, depending on the question. So I've got two versions for the questions where I'm doing one treatment versus another, and the ones where I'm pooling, right? So I've got two different MDEs for each outcome. And then I'm just giving you the ICC and the standard deviation for that variable. So again, the ICC is going to be different for every different variable that I'm using as an outcome measure. So I have to do this differently for each variable. Okay? Yeah.
So I guess for continuous data points, we're in sort of absolute numbers. But what if it's sort of a binary, if it's a pass, fail sort of, are we looking at sort of past percentages at that point? I mean, sort of how does that translate?
Yeah, so you just do, you know, the outcome is, say, the percentage, or in a sense, it's the probability that you would, you know, say we're doing, have I got, no, so I could do whether married by 18, right? And then it would be, then I'd look at the data of the percentage of people who are married, but in a sense, what I'm, if you think about it at the individual level, it's what's the probability that she would be married before 18. So actually, where you can, it's better to translate it into a continuous variable. It's the kind of funny things that sometimes happen at the ends of the distribution on a binary. And you have a little bit more power sometimes, where you have a continuous. So I prefer to do it on age of marriage rather than child marriage. But, you know, in the end, in the analysis paper we're writing, we show both. So, you know, these are the different variables, and I've got it, as I say, for the different, they're all measured. I prefer to do my power equations for the actual outcome, not in standard deviations, because I think it's very hard to think about that. You know, you know, when you plug it in, you do a standardized effect size, but when you show it and you think about it, think about the actual underlying variable here, right? Because we have a better intuition of what's a big enough effect to make sense when we think about the actual underlying variable. So in this case, you know, age at marriage, we can pick up 0.09 of a year. Well, that's pretty small, right? But if I put it in standard deviations, you wouldn't know what that meant at all. You know, number of births, number of kids, we can pick up 0.1 of a kid difference, right? That you know whether that's big or small. You have some intuition of whether that's big or small. Put it in standard deviations, it's much harder to think about it, I think. You know, so as I say, and then this is, you know, we're talking about 0.09 impact on the average of 18 years. So, you know, that's a pretty precise estimate that we're going to be able to get. Now, that's not true of everything. Like, we're not going to actually be, we don't have anything like as much power for the number of antenatal visits. I'm still going to measure it because I'm doing all this work, I might as well measure it. But I know going in that, you know, it's 0.18 on a mean of 3. That's not as good. But it's not my main outcome variable. I'm still going to do a power analysis of it, but it's not my main outcome variable. Okay, so which statement is not correct? And I'll have to think very hard to make sure I get this right. In general, cheaper programs can be tested with smaller sample sizes. When calculating MDE, we need to think about likely take-up rates. A smaller MDE means the effect will be estimated more precisely, all else equal. MDE has a big influence on power for a given sample size. Which of those? Most of them are correct. Which is not correct? Okay. A is not correct. In general, cheaper programs, we're going to want a smaller MDE because it's more interesting. You know, even if they have a small effect, that can be a pretty good effect because you're not spending much money. So you need to be able to pick up a small effect. So you need a big sample size. So it's kind of funny that you need an expensive evaluation to evaluate a cheap program, but that's the way it is. Because, you know, if a deworming pill costs 10 cents, you know, it can be incredibly powerful and important, even if it has a tiny effect. So you're going to need a big sample to pick up the tiny effect. If you're going to throw millions of dollars at a village, you don't need very many villages because if you have a small effect, I don't care. I really don't care if you have a small effect if you've thrown, you know, $5 million at it, at one village. Like, so the small programs are going to be harder to evaluate because you need to be precise to find their, to pick up a small effect. I mean, maybe they end up having a big effect, that's fine, but you need to be able to pick up a small effect if the true effect is small. So again, it's not about what you expect, it's not about what people have found in the past, it's about how small an impact you want to be able to distinguish from 0. So I'm just very quickly going to go over how you do this in this different statistical packages, and this is going to change as packages change. So always, you know, keep your eyes open for changes as you do these things. State has a new command power, which I am very disappointed about because the nice thing about it is you can do it different ways. You can state sample size and get out power. The problem is it doesn't allow for clustering. So for me, I kind of never can use it. So most people use the old versions of the old commands that we use to look at this issue, which is SAMPSci and SAMPCLUS. Those are add-ons to SATA, and cluster SAMPSci. The default in those programs is that power is 90 and significance is 5%. If you want to change that, you can. If you don't say anything, it will just give you those. So, you know, what do you do? I mean, you'll go over this with your TAs, but what do you do if you want to detect an increase in the average test scores from 43 to 45%? And that was our original example with a power of 8 of 80%. You would write samp psi, and this is the, you know, average in the control, average in the treatment. You want to be able to pick up, so your MDE is the difference between those two. Power 0.8, that's the SD is the standard deviation, right?
So if you're doing it for a continuous variable, you need to specify the standard deviation.
Okay.
And you can do SC1 or SC2 depending on whether you have differences.
Okay. You can see I get my RAs to do this. Stata gives, to actually do the coding, Stata gives n per cell, as we talked about before, the sample size per cell. So it will say N1 is 99. With multiple arms, again, as I said before, we need to multiply by the number of cells, the number of treatments plus control. And for binary outcomes, your standard deviation is going to be determined by the mean. Oh, yes. That was why I was being confused by this, because I was thinking that was the 5 was the significance, and that's not the significance. But remember, the significance is 5% by default, so I don't need to say anything. OK, I do specify power as 0.8 because their power is 90, and I don't want that default. I want 80. Power in Stata with clustering. We first calculate the sample size without clustering, and then you do an add-on. So in the above experiment, if you were to randomize at the class level with 60 per class and an ICC of 0.2, you do exactly the same thing that you just did, right? Assume it's an individual, and then you'd add samp class. You do another command for samp class, telling them about what the clustering is, the observations per cluster, and the row. And in optimal design, this is a special software that's designed for doing power calculations. MDE must be entered in a standardized effect size. So remember, the 43 and the 45, those were the test scores. They were not standardized. This, you have to put it in standardized. And the nice thing about OD, the reason I use OD is it allows clustering at multiple levels. So I sometimes have 3 levels of clustering. I did constituency level and polling center level, and then individual. So I had data at all 3 levels, and Stata can't cope with that, but OD can.